So the first part is basically about designing efficient heuristic for solving large-scale resource allocation problem. So you will really fast understand that actually all the resource allocation problems are what we call NP-hard problems, in the sense that after 10 instances, it's just not working. So there is a lot of research in the past decades that was about designing better heuristic and also being able to prove their optimality. And the moment you also add the dynamical aspect, everything is getting messier and everything is getting more complicated, but still people have been able to show some kind of nice heuristic. And the first part of the class is about understanding the different heuristics and algorithms that can be used there, and also try to prove their efficiency in some sense, okay? So first, in day one, I will just, start with kind of show you some problem in a resource allocation problem, and just kind of give you a brief recall of what is an MDP, and we will do some kind of simple calculation just to remember a bit what is an MDP and so on. And then hopefully we'll be able to finish with the first, and actually one of the most famous two and day three is just about complexifying this problem, right? So we will add more complex constraints. The problem is that at the end, it's still a polynomial algorithm most of the times that we're using. And therefore, we can ask ourselves the question how to do it efficiently, especially if some parameters are unknown. So this is what we'll see on day 4. And day 5, I felt obliged that with all this hype of machine learning and so on, to talk a bit about deep learning for resource allocation, to show you basically what can be done and what can be expected from deep learning and what cannot be expected. Okay, so basically the first part, you have to assume that all the parameters of the system are known, and still the problem is really hard. And the second part, parameters are not known, and we try to, in some sense, be able to deal with it. Okay, okay. So what you will learn in the first part of the class, kind of a general methodology to design a heuristic, and kind of have all the mathematical tools to prove that they are asymptotically optimal, okay? And you will also have lab session. So how works the lab session? I will just give you a notebook in Python. Actually, it's not hard at all. Huh? You just have, there will be some, you will have to fill some places and there will be some question. And then the day after, I will just give you the correction. Really, the goal is that at the end, you have some kind of small code to just use it to study it on your problem, okay? And for machine learning, the machine learning part, I will just give you some kind of brief recall on the classical result in gradient descent type algorithm. And then I will also tell you what you can expect from neural networks from a theoretical point of view. And then we will just implement some neural networks and deep reinforcement learning algorithm to solve resource allocation problem. Okay. Okay. So I think now I will slowly start with the example. So what I will just do now, I will give you briefly 2 examples to classical bandit problem, restless bandit problem. And then I will just tell you all the application. So please do not hesitate to interrupt me if you have any question at some point. So I will stop and try to explain you. So it's important that really these first hours, you're able to grasp and understand everything, because this one is easy and then it will get more complicated over time, okay? I will do a small break of 5 minutes at 10, and then we will go back, and then there is a half an hour break. So the classic problem, a classical example, when you actually not just resource allocation problem, is what we call the machine maintenance problem. It's kind of the toy examples that everyone knows when they do an MTP. So it's kind of an idealistic situation, and I will explain you why, but it's already a hard problem. So imagine that you have n machines which deteriorate under usage, and it's maintained by a set of alpha repairmen, okay? So you have to understand that actually, when you work with sensors, when you work in a fabric or in an industry and so on, all your machine needs to be recalibrated periodically. And in some sense, this is kind of the questions that we ask ourselves here. You have n machine which are in a given state, and you ask yourself, when should I recalibrate them? Okay. But the problem is you have a finite budget of repairmen, because it's costing a lot to recalibrate a machine and so on. So let's say that you have alpha of them at each instant t. And the question that you ask yourself is, knowing the state of each machine, how to minimize the total expected deterioration of the machine. Okay. So a naive policy, what would be a good policy or naive policies for this problem? Does someone has an answer? You have to speak a bit louder. What does it mean, a threshold policy? You have to be more explicit. What is the threshold and so on? And what do you do for the other machine? How you deal with the fact that you have alpha repairmen? Right now, it's a good policy for one machine. You just say, if I had one machine, what you would do is after one state, I'm always trying to recover. Yes. Really good. So this is actually a good policy, is basically take care of the ones that are in the worst states, and then check whether or not and just allocate alpha of them, right? So this is a good answer, but actually proving that is actually quite hard. So actually, the tools that I will show you today will show exactly that asymptotically, it is optimal to do that, right? But I don't have an answer whether or not it's optimal to do it this when you don't have a finite number of machines. So I know that this is optimal when n is going to infinity, the number of machines, right? But otherwise, I'm not sure. Okay, good. So let's try to be a bit more precise with the notation. So I will just try to keep it as simple as possible. Let's say that Sk of t is basically living in a finite set, which is the state of the machine of the machine k, right, at time t. And basically, the greater the value of Sk is, the worse the machine k performs. Okay. So what we'll assume in all our model is what we call the Markov property, in the sense that the evolution of the state of the machine k is modeled by what we call the control Markov chain. And what are the action is that a repairman is checking the machine k, which is action 1 for the machine A, and if it's not checking, then the action is 0 for machine k. So what we can simply do is write the following Markov chain, saying that the probability that at t plus 1 machine k is in a good state, knowing that machine was in a state S and that your repair is 1. So basically, when the repair guy is just going, is kind of able to reset completely the machine, right? And otherwise, you just degrade with a certain probability distribution. Okay. One thing is actually this model is a toy problem, and you will never use it in industry. Can someone tell me why? No, you don't have ideas? Ah, okay. So I'm saying that this model is really a toy model, and you will never use it in the industry. What is the assumption that actually is killing everything, which is making it not usable? The Markov property, you are saying. No, this is okay. I never say that the probability is stationary. Yeah, exactly. The fact that the number of states is finite and that you know them is actually not happening, right? Because what we are saying is you are designing an action at every point of time, knowing the entire state of every machine. But actually in industry, what will happen is you will have only a partial vision of the states, right? And even defining what is a partial vision of a state is actually tricky. So because I'm also teaching to engineers, I will tell you what I'm usually telling them is that there is a difference between doing nice math and so on and actually implement on a real system. In a guy who is an engineer and want to use this kind of algorithm has actually have to ask the following question. What is the state? What is the observation? And how to design it properly? And this is actually really, really hard problem. And actually, this is kind of how, if you are not able to set that correctly, all the theory is completely useless. But us, because we want to kind of design already some nice intuition and nice empirical results, a nice theoretical result, we'll not care about that. Okay. So now another important problem, which is for charging vehicles, which is also for networking and so on, is what we call the deadline scheduling. So imagine that you have a charging station, right, that has n charging spots, and they have enough power to charge m vehicles at each round, okay? So what we will assume is when a charging spot is available, a new vehicle may join the system and occupy the spot, right? So I'm not saying that someone will always come when there is an empty spot. I'm just saying that with a certain probability, someone new will come, right? And then the moment the vehicle is occupying the spot, the vehicle will announce these two things. First, when he wants to leave the station, I will stay 1 hour. I will stay 1 hour in the station, and the amount of electricity that it needs. Okay, so you can also imagine the same thing when you go. You're in the same thing networking, where you have jobs coming in a data center, and the job can tell you, I want this job done in certain hours. 1 hour. Let's say that I have my neural networks to train, and I'm giving it to Google. I will tell that I want to that you train my neural network in 1 hour, and this is the amount of bandwidth that I need. So this is kind of the same problem. Okay. This is just discrete time. So there is we do everything in discrete time. So, okay, so in this model, nobody can come if there is no empty spot. Yeah. Yeah. Okay. So what is the reward and the cost in this case? You assume that the charging station obtains a reward of 1 minus C for each of unit of electricity provided to the vehicles. Okay, so basically each time I'm able to improve a bit my, for example, the give electricity of when we talk about machine learning, train a bit better my network, we give a reward. So it's not great. Huh? It's just kind of we have to design this reward. And the other thing is assuming that the station is not able to complete the task before the deadline, then the station needs to pay a penalty, which is proportionally to the amount of unfulfilled charge. Okay, so I think it's clear for everyone. So in this case, the question is not about admitting, So basically, when you have a slot open, you have to ask yourself. So in this case, it's not an admission problem, I'm sorry. In this case, it's more assuming that I have electricity resource, right? And at each time, I'm asking myself, should I give it to this spot or not? Right? It's more a kind of, you have multiple spots, you have a finite resource, and you ask yourself how to devise my resource such that I'm maximizing the charging and such that I'm respecting this cost. Just the value. So you have to understand that when we do MDP, we kind of create rewards that sometimes do not have physical meanings. It's just that to incentivize the fact that the charging station have to provide energy to vehicles. Okay. Oh, I don't know. I have to. yeah. Basically, it's from this paper, and I didn't think too much. You can clearly simplify it, but yeah. No. So they give automatic. So it's like imagine that you are actually going to get some petrol, right? What's happening? If you see that all the slots are full in this model, at least you just say, I'm going to another one because I don't want to wait, because I'm not aware. So the moment there is an empty spot, someone is coming to fill in. And then your only question is, I have like this huge battery, let's say, and I'm asking myself, at this time unit, do I give to this guy or not, right? So, okay, perhaps an easier way to see this problem is imagine that you have some water, right? And you have a set of houses, and you have n houses, and at some point a guy is asking for water, and you have to decide whether or not you are giving to him or not, knowing that you have a finite resources of water, right? Something like that, yeah. No, it's not denying it. So the entries, they don't deny the entry, but they don't charge at every time instant. It's not because you're in a slot that you always receive electricity at time t, right? Sometimes, so it's a bit like, they process. Do you want to take care of this job or not? And they can decide. Just being in a queue, imagine that each slot is a queue of a buffer of size 1, and you just ask yourself whether or not you are serving or not. That's it. Yeah. Yeah. Exactly. And you have also be a bit careful because you have to imagine, it's exactly that. And you have to be a bit careful because perhaps if someone is coming with a short deadline, then in some sense, you will have to prioritize him to give everything, because otherwise you will have a huge cost. But the other one with a low deadline, you have also to be sure that you are able to take care of them at some point. So this is kind of the problem. So how do we model it as a Markov chain? So let's say that Tk of t is equal to the lead time until the deadline, to the deadline decay, sorry. So it's dk minus t, where dk is the deadline imposed by the car in station k. And bk of t is the amount of electricity required, right? And what is the state of the chaos spot? It is 0, 0 if there is no job, right? So I think that for everyone is good. And otherwise, it is the lead time to the deadline and the amount of electricity that has already received the current slot K. And the evolution is quite simple, actually. So at t plus 1, basically, your lead time is reducing by -1, so I'm getting closer and closer to the deadline. And then it is equal to the amount of electricity that I need minus whether or not I've been served with a certain amount of electricity, right? So that's it. And when you are 0, 0, when the deadline is 0, basically there is a certain probability that someone is coming up with a given deadline and a given load. So I will wait. And just remember that AKT is the amount of electricity given to the spot K at instant T. And AK is actually your action. So you see that basically you have to allocate really smartly the electricity among the different spots to be sure that you're able to respect the deadline. So is the model clear for everyone now? Yeah. This one? So when TKT is equal to 0, it means that the guy is leaving, right? So when it's leaving, it's just describing the arrival process. So with a certain probability, exactly. No. So this is why I'm telling you that there is not really an admission problem there. If you want to have admission, you need to add a control also here. Okay. Okay. So this is 2 applications, and actually all the 2 problems that I've shown you can be considered a really important problem, but actually are known to be NPR. So assuming that I'm giving you K, for example, I don't have any clue or any simple intuition about what should be the strategies there, right? We cannot apply we cannot apply just give electricity to the one with the slowest deadline, right? Because there is also the amount of electricity remaining, right? So we actually don't know what to do there. So even if all the station, all the spots are symmetric and so on, this problem is actually NPR. And our entire goal today is to find a way. So the only goal of today is to learn how to design an efficient heuristic to solve such problems. So both of these problems that I presented today. So you have other applications there. And there is some references that quote all of them, depending on what you would like to apply to these tools. You have some application in wireless communication, web crawling, congestion control, queuing system, cluster and cloud computing, target tracking, and clinical trial. And you can have many more of them. Even I think epidemic, some sense control can be framed in this framework and so on. So what I will just do is briefly some kind of small background. So I will go a bit fast because I want to know, everyone is familiar with Markov chain here? But okay, so then I will just go fast. So I will not even go there. So this is just, so let's start even thinking of multiple slot problem. Let's just start with a simple MDP and study some property of it. So I will say that a one-arm restless bandit is a NDP, which is defined on a finite state space. A finite set of action. So let's say that for simplicity, you have 2 actions, 0, 1. So of course, as long as it's finite, everything that I will say can work also. So basically what's happening I will describe now the decision process. And this is something I think that when one wants to model, even if one wants to model a real world problem, it's really important to detail exactly, to do always this process, because even if you know that it's a Markov decision process, you always have to ask yourself is when do I take the action, knowing what, and so on and so forth. So this is kind of an easy way of modeling your problem. So the decision maker gets full knowledge of the current state of the system S of t, right? And when S of t has been observed, the decision maker chooses the control A of t. He receives a reward, right, which is depending on the current state and the action. And then the Markov process evolves to the state S prime with a given probability, which is depending on the previous state and the action. So why? And the objective is to maximize the expected total sum of reward over t time steps. So we are not doing discounted. We are not doing average cost. We are doing finite horizon. So why I'm saying that it's important to always do that? Because actually there is some words that you have to be really careful. For example, in a lot of problems, ST has not been observed explicitly, right? So you have to be careful with that. Do you have full knowledge of the system? Not always. The reward in this case, yes, most of the time you have it, and that's it. Another important thing that you have to understand is we are not in a reinforcement learning framework. Why? Because you know the reward, you know the entire reward for every state and action, and you know the transition matrix. Actually, if you are in a reinforcement learning framework, so for people that know a bit about it and that do OpenAI gym and so on, actually it's working exactly like that. However, you don't know the reward and you don't know the transition matrix, right? Okay. So another thing when one is working with a dynamic optimization problem is we have to define a policy, okay? So the general control policy is basically would be a mapping from each possible what we call history. So basically at time t, you look at everything that happened in the past and you decide what to do. But the problem is you have to be able to do a mapping from every type of history. So what you can guess is the moment that you are going, so h of t is growing exponentially. So there is no way that you can do that, okay? So usually what people do is they use kind of Markov control policy, right? So basically you just say that my action is only depending on my current state. And what you can even do, and this is what we'll use most of the time in the class, is that you can choose randomized control policy, where basically, which are Markov, is your action is not a deterministic action, but it's random. And actually, this is helping a lot to achieve optimality, okay? So one point is actually, why Markov? A practical reason is just the simple type of policies that you can use, right? Because you know that you cannot do based on history. So you're like, what is the second next things to do is to just doing depending on the state. But actually, in a lot of problems, it has been shown that it's reaching the optimum, right? In a classical MDP and constraint MDP, as long as you add randomization in it. Okay. So in general, it's given HT, but what we'll use is given ST. Okay. And just for being clear about the transition matrix now, that the probability to go to S prime at t plus 1, knowing A of t and S of t, given a randomized policy, is simply the probability to go to S to S prime when action A is taken, multiplied by the probability that at S, I'm playing A. Okay. Okay. Very good. So now we just define the cumulative reward. So usually the classical MDP, tell me. Mm. Yeah. No, exactly. No problem. So what will work today is with cumulative reward, in the sense that we are interested in minimizing the expectation from t equal to 0 to t minus 1 of my reward, of the sum of my reward. But one of the reasons we are doing that is because for a class, actually, it's kind of the easiest way to do the math. But you can imagine a lot of things there. And actually, you should not limit yourself to cumulative reward. In a lot of problems, for example, what we are interested in is the probability that to reach a target in the minimum amount of time, things like that. So just remember that cumulative is not everything. It's just for mathematicians a convenient way of working some simple and elegant results. So this is our reward for a given policy PI. So I will not always define all my reward, but note that when I'm using a P here, it means that I will place my Markov chain with a policy P. And the value function, when I'm using star or there is no pi there, sorry, not P, pi, then it means that I've taken the minimum, right? So basically what we define the value function to be is basically the best policy, which is minimizing my value function, right? Policies, right? So it's not clear how to solve it. So most of you of a Markov chain. So let's define the following linear programming problem. Yeah. Ah, yes, it's okay. I'm sorry for that, but I'm saying that it's okay. I think all of you knows that if I put R, we minimize everything in this class. And if we don't minimize and you think it's maximized, then we maximize everything. So sometimes, you know, in this thing, depending on the problem, we alternate between minimization and maximization. And we do such mistake. Okay, but most likely I like to minimize. Okay. I'm not a positive guy, I'm more negative. So let's define the following linear programming problem, right? So let's a bit have a look at this linear problem. What do we have? So we have our cost function, and you have this variable y a of st. So y of a of st can be interpreted as the expectation on the entire trajectory that I will play A when I know when I'm in state S at time t. So I will write all this. This is just kind of part, these two terms are part of what we call a continuity equation. It's related to the Kolmogorov equation. And this is just the initial state. So I will show you now that assuming that you solve this LP problem, I will come back to it. So this is why I skip this slide, because I feel that doing the proof will help better. Okay, so let's say that you have, what we'll prove now is that when Y star is a solution of the LP, then taking this policy, which is Y star divided by X star, where X star, there is stars there, I'm sorry, where X star is the summation of the Y, so basically it's this point, right? Then you obtain your optimal policy. Just wanted to know who knows this theorem? Well, I mean this lemma. Nobody is? Okay, really good. So if someone knows, I would like to know. Yeah, no, really nobody. Okay, really good. So now we will do the proof of this theorem here. Okay. So I will call Y of S A T. Does everyone see? Yeah? Okay. Equal to the expectation of playing the expectation of this event. AT is equal to A, and ST is equal to S, knowing the entire event. So knowing basically X0 equal X0, right? And I will also define MS of T, which is the expectation of S of T equal S, knowing X0 equal X0. Basically the initial distribution. Okay. So, very good. So what is the expectation of an indicator function? Really good. Good. You always, so this we know is just the probability of having A of T is equal to A, S of T is equal to S, knowing X0 equal X0, and the probability of S of T is equal to S, and X0 equal X0. So now we will just use actually the Kolmogorov equation to just obtain this, this function. So the first thing that you have to observe is the following, right? So why the probability of A of T is equal to A, knowing S of T, knowing X0 equal X0, is just equal to the probability of A of T equal A, knowing S of T equal S, because it's Markov, I don't care, multiplied by the probability of S of T equal S, knowing X0. So it's coming from Bayes' law. So then we already see that we are kind of in a good shape, right? Because the thing is, if I just take the summation over all A, what's happening? So let's call this, as I say, ASA of T. Then if I take the sum, what's happening is the summation of AS of T over the A is equal to I'm just taking a summation over the A there. So I can factorize by this probability, and the summation is equal to 1, right? So basically, it's just equal to MS of T, right? So we get these first constraints. Okay. Okay. So I'm really limited to the no, because yeah, I can go. Okay, thank you so much. So then the only question remaining in some sense is what to do with the probability that MS of T, not MS of T, I'm already doing something else. S of T is equal to M, knowing that the initial distribution, X0 equal X0, or basically S0, I'm sorry, I'm changing notation now, equal S0. So this, just to recall you, is just MS of T. Really good. So what can we do? So this is simply equal to the summation of a S prime and A of the probability of, the probability of AT Let me try to write it properly for you. Tac, tac, tac. Okay. Okay. So this is the probability that I will play at minus 1 equal A, knowing S of t minus 1, which is equal to S prime, and the probability that S of t minus 1. Okay, so this is one good thing. Yes, no. I should not do this decomposition. I'm sorry. The simpler decomposition is this one, that I'm playing t minus 1 and I'm in state S, right? Multiply by the probability to go from S of t is equal to S prime, knowing S of t minus 1 is equal to S, and A of t is equal to A t minus 1, I'm sorry, is equal to A. So what I just said is I've just used the law of total probability to just, so this is simply the transition matrix, right? So this is probability of going from S prime to S multiplied by A. And then why I wanted to have this decomposition, because actually it's our definition of Y, right? And what we get there is simply by just rewriting with the right value, is that this is equal to Y of SA. How did I write it? Yeah. Did I write it like that? Well, it's okay. Y of SA multiply. Yeah. You want I make it bigger? Okay, no problem. So there you were able to see? Okay. What I was just saying is the following. M S of t plus 1 is equal to the summation of S prime A of the probability that A of t equal A and S of t equal S multiplied by the probability of S of t plus 1 equal S prime, knowing S of t equal S and A of t equal A. Okay. This is Y S prime I up, I'm sorry for this. And this is the probability to go from S prime to S in A. Okay. So basically, we have just recovered this formula. Okay. So you clearly see that you can express everything in terms of these two values. Okay. And to recover actually the control, remember what is the control is actually this probability, right? Is the probability to play A of t equal A, knowing S of t equal S. And therefore, you can see that you can divide Y by M. This is M, right? You can divide Y by M as long as M is not equal to 0 to get the policy. And this is how basically you prove this lemma. So I'm sorry if I'm not, I'm trying to give the big pictures. I hope that all of you have understood the proof at least, and you will be able to make the different steps yourself. Okay. So what does it mean? It means that we know that every Markov chain that in my example can be just captured by M and S. And I'm able to capture all types of policies just by M of S and using this decomposition, right? Therefore, if I'm able to solve my LP, because I'm optimizing on my entire space of policy, then automatically I will be able to find the optimal value of my problem, which is V1. I think I've called it V1, yeah, V1. V1 star, so there is a star missing there. Okay. So basically, solving an MDP is solving a LP, okay, in finite state space. And actually, all this can be done when the state space is continuous, right? The only thing is you will work in weird space, right? So you will have to define the right topology and the right metric to define everything. So one thing that I would like you to notice is that the number of constraints is basically here for every t. So you have t multiplied by the length, the size of the S, right? And then this one is also the same. So you have the number of constraints is of the order basically 2 multiplied by t and the number of states, right? So the problem is, in the first problems that we have seen, the one arm bandit problem, it's kind of easy, right? Because you have just one machine that you want to repair. But the moment you have multiple machines, actually S is going to grow exponentially, right? It's of the order basically S at the power n. And therefore the number of constraints is just exponentially. So this is why it's, even if you know that you can solve it using a linear program, your computer will just not be able to do it if you go, for example, to n more than 5 or 10. Okay. And this is why people have used some heuristics to solve this problem. Okay. So now, okay, really good. We will have time to do everything. So now I will actually talk about the real problem, which is a finite horizon restless bandit. So before I switch there, is it okay for, all of you have been able to understand the LP formulation of a MDP? Is there some questions? It's okay if there is some question, we have time. Okay, yeah. You don't get this formula? I'm not sure to understand your question. Can you be? Why you multiply this and this? I'm sorry, I'm not able to listen. You have to speak really more loudly. Ah. 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 You don't understand this, basically. So, do you agree with the first line? Do you agree with this? You agree with this or you don't agree with this? I'm not sure to understand, but perhaps I will take a bit time to explain where it's coming from, and let's see. Okay. So I will remove the conditional expectation with respect to the initial condition to simplify my life. So basically, I want to study this, right? Okay. You can always say that this is equal to S prime A, probability of S of t plus 1 is equal to S, knowing A of t is equal to A, knowing and not knowing, and S of t is equal to S prime. Okay? So now let's look a bit at this. So this, you can always say that it's the probability of having S of t plus 1 is equal to S, knowing A of t is equal to A, S of t is equal to S prime, multiplied by the probability of A of t is equal to A and S of t is equal to S prime. Just by Bayes theorem. And that's it, right? Because this is the transition matrix, right? So this we know, right? Because it's a Markov chain, S prime S of A. And this is our parameter, A S of prime. Okay. Really good. So perhaps we can take a 2 minutes break, a 5 minutes break, and then I will switch to the other problem if it's okay for you. Okay. Yeah. So, Tariman is the speed. Two and a three is just about complexifying this problem. If one machine what you do is after some certain steps, and something imagine, yeah, it's a bit better to make
May I request everyone to keep their microphones on mute? Uh, it may create some disturbance in the lecture. Right now, we are on a short 10-minute break. I also request you to keep your questions to the end, and the instructor will be able to take your questions only at the end. Thank you.
a couple of announcements. So this online viewer, please keep yourself, muted so that you don't disturb the lecture. Second thing is, yeah, I think it's fine. Second is that there will be coffee at 11. So, just so there will be some refreshments. And if you're really, feeling that you need coffee, you can take. Please do not drink inside. Take your beverages outside. Do not enter the room with this. Yeah. And if you really feel like you want to have coffee, there's a coffee machine outside. You have to pay 10 rupees to the EC office, and you can take a cup. You can drink, but please drink it outside. Do not bring inside the classroom. Yeah. Okay.
Okay.
So a couple of announcements from my side too. So there is a poster presentation in the ECE main lobby. It displays the work conducted by the CNI PhD fellows. So you can go there during your coffee break from 11 a.m. to 11:30 a.m. Interact with them and get to know about their research. Second announcement, please make sure to sign this attendance sheet during the session. If it does not reach you, you can sign it at the end of the session. But please make sure to sign this attendance sheet. Okay, thank you.
Okay. We'll start again. So just Parimal told me that, and it was good to telling me that I think I've made some, the proof was good, but there were, at some point I add notation and so on. So I will be a bit more careful. I'm sorry for that. And for the next proof, I will be much more careful. Okay. Okay, so let's talk now about really the problems that is of interest to us today, which is what we call the N-arms restless bandit problem. Okay, so some of you that are coming from the machine learning community and the statistic community will think that, oh, I know bandits, and the distribution we at least from what I know in machine learning and statistics, don't tackle so much this problem is basically you have n statistical statistical equivalent MDP. So there is a missing word there. So basically, every arm has the same MDP with the same transition probability. Why we do that? Actually, we don't need to do that, but to do the math, we need this kind of symmetry. Okay. And how does it work? So SK is the state of the arm K at the discrete decision time T. Okay. I will denote by AK of T the action taken by the decision maker at the discrete decision time T also. Okay. And what we assume is that for when you give AK, the dynamic, when you give the actions that you apply to the arm K, the evolution of SK is only determined by its own evolution, in the sense that it's not because I have an arm in K primes that is in a given state that I will impact the probability distribution of an arm in a state K. So the only coupling between the different arms, right, are through the action. And this is actually extremely important. Okay. And what we assume is that the decision maker have to choose only a fraction of arms to be activated. So what does it mean? It means that AK activated means that AK should be equal to 1. So I can put at every time instant only a fraction of arm at AK equal to 1, which is equal to alpha. Okay. So more precisely, how it works. So the decision maker get full knowledge of the current state of the system. So you see that you are in a product space, right? Then once the state has been observed, the decision maker chooses a control A of T right? For every arm, he decided to activate them or not. And we will assume that the number of arms that can be activated should be smaller or equal to n alpha. So basically, in average, you should only activate alpha arms, okay? And the decision maker collects the reward for every arms, okay? And is interested in maximizing the sum. Finally, as I said, when the action is fixed, the probability that Sk at time t plus 1 is equal to S prime is only depending on its own transition probability and on its previous state, okay? The goal is to maximize the expected total sum of rewards over the t time steps. And we know everything, okay? So one thing is that the problem is you see that you are living in a space of the size S at the power n. So the representation of the state is quite tricky. Designing a control, just imagine that I'm designing a control P, which is going basically, which is a mapping, which is going from S at the power n, right, to A at the power n, right? The problem is if I want to do some kind of limiting behavior or even some kind of, even I would like just to transfer my P to a bigger state space, right? When n plus 1, you see that it's not easy, right? Because you see that we are not living in the same space. Sometimes you can be n, sometimes you can be n prime. And because we want to understand what's happening when n is going to infinity, we will derive a new state representation for our MDP. Okay. What we are saying is that arms are exchangeable in the sense that two arms that are in the same state and for which the same action is chosen will provide the same reward and have the same transition probability. So this is kind of the main assumption to make everything work, right? So everything is symmetric. And still the problem is hard. No? So what does it mean? It means that instead of just applying your control directly on your state S of t, right? You can directly work on the empirical distribution of the state at time t, right? So because there is no difference in the information that they contain. So now I will denote ms n of t being the fraction of arms in state S at time t, right? And basically I'm defining the associated vector. So another definition of MSN of t is just the summation from k is equal to 1 to n of the arm that at time t are in state S. So this is just the empirical distribution of the states, okay? So what is really nice is now you always leave ms, the vector that I define there, m on nt, is always living in the simplex for every n, right? What does it mean? The simplex of time n minus 1, which where basically it's a probability distribution, right? So this is all the x in 0, 1, n, such that xk is positive, and the summation of x prime of xk prime is equal to 1. So basically, you are working in a measure space now, okay? And now we do all our control on this vector m, and note that whatever, sorry, there is no n. The dimension is the dimension of the MDP, so it's S minus 1, S minus 1. K is equal, yeah. So this is S, this is S, and this is S, right? because basically it is what is the probability at instant t that I'm in state S, right? So we are living in this space, and you see that actually this space is not depending on n, right? Because this fraction we just refine, the more n is growing, this empirical distribution will refine, the more n is growing, but otherwise we are always living in this space. So it's really good in terms of maths because we don't have this weird change of space and so on and so forth. Okay. So now I will define something else, which is YSAN, which is similar to what we have seen before, which is the fraction of arms in state S and at time t, for which the decision A has been taken, right? So this is the two notations that I will be using. And you can start to have the feeling that at some point a LP will come out again, because actually I'm using the same notation, right? So now what is the mathematical formulation of this problem? The restless bandit with n arms. I'm trying to, oh, the expectation should be there, but it's okay. I'm trying to maximize my reward, right? Depending on the fraction of arms that where I play A and S at time t, with my classical constraints, right? What I'm saying is I'm taking the fraction of at time t, I'm looking at the fraction of states that are in S, right? Of arms that are in S, and I'm saying some of them I will play 0, some of them I will play 1. So this equality is coming from there. So this is the budget equality, the ones that we have seen before, right? There is not an n anymore there because we are working with fraction. And then I have my classical dynamics, okay? And then I have the initial condition. So this is the classical n-arm restless bandit. And actually, all the first two problems that we have defined at the beginning of this class are exactly belonging to this framework. You can just write the math, write the transition probability, and so on, and it's exactly that. Okay. So the K difficulty is there is a coupling due to these constraints, right? Because we want that at every time, only at every time, we want that with probability 1, in the sense it's not even probabilistic, I'm only playing action A n alpha time. So basically, I only, the proportion of arms that where I'm playing A at every time should be lesser than alpha. And the problem with this constraint is, first of all, try to write this event. You will see that it's just a product of probabilities, it's horrible. So you cannot exactly quantify this event as such. And also, so it's extremely combinatorial. And also, the problem is, even if you want to quantify in terms of probability, actually, I'm telling you, it's a hard constraint. You cannot do anything about it. You have to satisfy this constraint no matter what. Okay? And this is what is making the problem difficult. This is where the coupling is happening. And this is why the problem is NPR. And the challenge of today is how to design an efficient heuristic to solve such problem. Okay? Does someone has an idea? So when you do stochastic programming with stochastic constraints, what do you do usually? Nobody knows? Usually you relax the constraints, right? Because working with such constraints, you find a way to simplify these constraints, hoping that at infinity, you are exactly matching the constraints. Okay. So this is what we call relaxation, and this is a classical approach that have been taken through the entire literature of restless bandit. So instead of wanting to satisfy the constraint always, you just say, I want to satisfy the constraints in expectation. Right. The problem, so let's see the problem that it will induce. The only thing, take a second of decision rules. Optimal. Okay. So the question is now, imagine that I'm relaxing my constraints. So basically, instead, before I didn't have any expectation. Now I want to have an expectation in this problem. The question is, what is the form of this problem? Okay. Why it's making the problem much simpler. So let's see why. Okay. Actually, what's happening is you can define a similar LP problem as before, which are the variables are a bit different. And yeah. Okay. Yeah. So for the people that are in the classroom, please speak much louder because I'm not able to listen to you. So what you wanted to say? Yeah, because I didn't talk about it actually. So, so this is why you are not able to follow. So listen to my voice and not too much to the slide, and it will be better. So the thing is, we can define a similar LP problem for the relaxed version. So actually, for when we don't relax the constraints, we cannot formulate as a LP. But when you formulate this as the relaxed problem, when you formulate as a LP, then what you can prove is actually that
point is that your optimization problem is the objective function expectation, right?
Yeah.
And your constraint was on random data.
Yeah.
Now because the expectation is a constraint, I can replace all the constraints.
Exactly, and I will prove that it's okay.
I think.
Okay. So perhaps if I have to write down, so this is a constraint 5D. Before, what we wanted to optimize, what was the constraints that we have to satisfy, is this one, right? Remember that this is a random variable. Yeah. Sorry. 1. So when you activate. Really good. So we want to satisfy this constraint, and this is a random variable. Just tell me how to sample. Even I'm asking a simple question, assuming that you know the distribution of these random variables, they are IID. Try to find a way of and you can control the mean. Try to find a way of sampling such that this is always true. Actually, it's not a trivial question, right? So we have ways, of course, of doing it, but you can clearly see that this is not a trivial question. And in the original bandit, actually, it was an equality constraint. In my case, for the class, I make it inequality because it's much easier. But even try to satisfy always this constraint with random variable, it's not tricky. And what we are doing in the relaxed problem is basically we're taking the expectation here, right? And this is much more easy to deal with, right? So the relaxed problem is not yet giving us, be careful, the relaxed problem is just another side problem, and it's not giving us yet what to do on the n-arm bandit problem. It's just a relaxed problem. I didn't tell you how to go there. Good. I don't need to relax. Which one? 5C. This one? No.
But in your next slide, that is also taking expectation.
No, it's not, because actually, I will explain you. I think it's quite easy to understand. Actually, you want everything in expectation, right? So you can apply the linearity of expectation to have something in expectation there, right? So what is happening is I have an expectation there. This is an equality with a sum. I can take expectation everywhere also. So basically, the moment I'm relaxing this, I will just work with expectation. And I will prove how to do that now. Okay. So let's do the proof. So again, I will define, so now I have to be a bit careful, just so that I'm not messing up again. So I will say that MSN of T. So as I say, it's a distribution, right? K equals 0 to N of the indicator of Sk of T is equal to S and AK of T. No, and that's it. Sorry. Okay. And I will define Yn of SA of T, which is equal to 1 over N summation over K of this function. Okay. The first thing that you have to note is that what we want to minimize the summation of a T equal to 0, the expectation of the summation of T equal to of T of S and A of Y, it's, yeah, R of SA, Y, yeah. Sorry, really good. Thank you. Okay. We want to minimize that. And basically just forget about the mean, but using the linearity of expectation, what you will simply have is T equals 0 to T minus 1 of R of SA, and the mean of Y of SAN, right? So basically what we see is to optimize our cost. The only thing that we should understand is basically, sorry, and there is a T there. There is a T here. And there is a T here. So the only thing that we should look at is the expectation of this random variable and understand its evolution over time. That's it. And what are the constraints? Okay. Well, the first constraint is this one, right? This one is fixed by the problem. Okay, really good. So now let's try to understand the dynamic of these two random variables. Okay. Actually, I think you know exactly what will happen, right? So if I define Y of SA of T, which is equal to the expectation of YSAN of T, again using the linearity of the expectation, what you will have is simply the probability of being in SAK of T equal S, and okay, no, I think I went a bit too fast and it will not help you, but because everything is symmetric, it's not changing anything. So the probability that arm K at time T is in S, and arm K, and you play action A at time T for arm K. Okay. Remember that all the arms are symmetric, right? So in some sense, I will be able to drop the subscript K here and here, and I will be able to remove the N. So, but let's see that later. So what's happening is that I have this formula, 1 over n summation from k is equal to 0 to n of the probability of sk t equal s and ak t equal a, which is equal to 1 over n, k equal to 0 to n. And then let's do a bit again the same type of things that we were doing before, right? Is that this is the probability. So okay, what probability I'm playing? I'm playing sk. I'm playing a when I know s. The probability is just a fraction, right? So what will happen is it will be just equal to the probability of playing ak the probability of playing ak knowing t, playing a and sk of t equal s multiplied by the probability sk of t equal s. Okay. Really good. So now the goal is just to notice that what you can do is, yeah. 1 second. 1 second, I'm working with YSA, huh? Okay. Okay. Tac. Okay. The thing to notice is that what you can do is you can take the sum over A, and what you will obtain is you will obtain that the summation in A of ys, how did I not? Okay, ysa of t is equal to 1 over n summation over k equal to 0 to n of the probability of sk of t equal s summation over a of the probability of ak of t is equal a, knowing sk of t is equal s. And this is equal to 1. Okay? So you simply have this. And therefore, this is simply, if you just rewrite the definition of M, this is simply M, no, yeah, 1 second. This is simply the expectation of this, right? Expectation of MSN of t. And I will denote it ms of t. Okay? So what we have proved is that if I define, so I will add 2 notations there, right? ms of t, it's equal to the expectation of msn of t, and ysa of t is equal to the expectation of ysan of t. Okay. And what we have just proved is that the summation over I of the expectation of the fraction of a state where we play I is equal to the expectation of the fraction at instant time of arms that are in state S. Okay. So now we have the first part. We have first expectation. So now the only thing that we have to understand now is the evolution of MS, right? We have been able to deal with this constraint because it's an expectation. In some sense, we have been able to put these constraints in expectation, right? And now we just have to understand the evolution of M. Okay. Can I erase there? Okay, really good. So what do we have is we have M S of t, which is equal 1 over n, summation over k equals 0 to n, of the probability of sk t plus s of t is equal to s, right? And this is nothing more than just by using the Markov property and the total probability rule, then the probability of sk of t is equal to s, knowing sk of t minus 1 is equal to s prime, and ak of t minus 1 is equal to a. If I'm taking a summation over s prime and a here, multiply by the probability of sk of t minus 1 equal s prime, and ak of t minus 1 equal a. Okay. Really good. Is it good for everyone? Everyone is able to follow? Really good. So the good part is that this we know, right? Louder. Thank you. So this is just the transition, right? Okay. So what do I have? I have ms of t, which is equal to 1 over n, summation from k is equal to 0 to n, summation from s prime a of p s prime s a, and multiply by the probability of, what is it? Sk t minus 1 is equal to s prime, and ak t minus 1 is equal to a. And you can just revert the sum. You can just invert these two sum, right? And it's just summation over s prime a 1 over n, summation over k equals 0 to n of so here you put this of this. Right? I just revert the sum, right? Okay. Why? And you see the importance. Why? Because the transition probability for every arm is the same. So the moment I don't have that, I have asymmetry between my arms, I cannot do that actually, right? And therefore, this is simply equal to sum over A of P of S prime SA. And this you can, if you remember correctly, is nothing more than the expectation of playing the expectation of the fraction of state, sorry, C prime, right? And T minus 1. Thank you so much. Okay. So what we have just proved actually is we have been able to express everything in terms of expectation. And therefore, you can write this as a linear program. You are, of course, going through all the policies. And therefore, just by solving this linear program, you will be able to solve the relaxed problem. So what we have just proved is that the relaxed problem, when you put the constraint in expectation, is again equivalent to a LP. The other thing that you have to understand is what is the cost of relaxation, right? When you try to satisfy constraints in expectation, do you think that your set is bigger than when you try to have always satisfy this budget constraint for every type of event? Is it a bigger constraint or a lower constraint? And that's the set. Is it bigger or lower where you optimize? Exactly. So basically, you optimize in a bigger set, and therefore you can have a better minimum, and therefore you have naturally this. You will have V opt n, which is smaller than V real, right? And because V real is equal to VLP, so you already have a lower bound for your n arm bandwidth. Okay, really good. Now, what is the problem? So do you know how to design a control from this LP, from this relaxed problem for the n-armed problem or no? Do you have any ideas of what kind of the issue is? Okay. So let's see. So let's define the feasible control. The feasible control for a given empirical distribution should have the following property. First, you need that your proportion of arms that you are playing, the proportion of action that you are playing in a state S should be equal to the empirical distribution, right? You want that such that you don't, basically it's just kind of a continuity equation thing saying that imagine that I have a certain number of particles in state S and I will have to take action. I don't want to take more proportions that I should be, right? So this is the first constraint. And the second one is a budget constraints, right? I'm saying that I want to satisfy the proportion and I want to satisfy my budget constraints. So this is what we call a feasible set. And let's have some observation. Y star of T is the LP, the solution of the LP. Where I have D? Oh my God. D is S, the size of, D is S, I'm sorry. D is the size of the state. Exactly. I'm sorry. It's a good, good point. So let's say that Y star, yeah. One S1, it's the active. You want that, yeah, you understood. So proportional active should be even equal to alpha or smaller or equal to alpha, right? Okay. So let's say that Y of T is the solution of the LP. So basically it's saying that what is the proportion, it will give you what is the proportion of action at time T, what is the proportion of active arm and not active arm in the different states that you are playing at time T when you solve the LP. The big problem is that it's not belonging to the feasible set for a given distribution M of T, right? Remember that when we look at our real problem, we need these constraints, right? If this constraint is not satisfied, we are not solving the problem, right? So the first thing is the solution is not belonging to, so the LP solution is not belonging to the action. So actually the policies that you have learned, policies that you have learned on the LP, you cannot be using it for solving the NP-arm problem because actually it's not feasible. Okay. And the other problem is, no, and in general, what you have, so it's not a problem, it's a good thing, is, however, if you take the M, which is solution of the LP, right, which is a summation of the Y over the action, then it's feasible, right? Why? Because basically you are looking in a trajectory, in the mean trajectory, and you have designed a problem where for the mean trajectory, for the optimal mean trajectory, you should satisfy these constraints, right? It was in our LP. So the question is actually how to design some kind of transformation of Y such that it's feasible. This is kind of the challenge, such that we can apply to an arm problem. So kind of trivial way to doing is just to use a projection operator. So you say, I want to find the minimum Y, which is feasible, such that I'm as close as possible to the optimal solution in the LP problem. Why it's nice? Because projection, you will satisfy the feasibility for every N arm. And also, what is nice is when you are at M star, you will be equal to Y star. Okay? And this is the main trick. So does everyone understand why we're obliged to do that, or is there some issues? So relaxing in what sense? No. What we are saying is the following. I have an MDP with N arms. I don't know how to solve it. First, let me design a policy that has the following two properties. It is feasible for my MDP with N arms. This is the set calligraphic Y, right? And also, then when I'm close to the LP, when I'm equal to the, when my control is actually equal to the LP, I want to be the LP. So I want to be as close as possible to the, basically, okay, let me perhaps summarize it to give you a hint of what's happening. When N goes to infinity, actually, you converge to Y star. You converge to M star and Y, and therefore, when N goes to infinity, it's equivalent to solve the N arm problem. The only thing that you're asking is, I want a control which is feasible, and when I'm at infinity, should be equal to the LP problem. In some sense, you want a scaling property, right? I want that the more I'm getting close to infinity in terms of the number of arms, the more I should be close to the LP because I know it's the optimal solution. And the projection operator is actually doing that, right? This is ensuring feasibility. And this is saying, try to be as close as possible to Y star. It is not giving the solution for the MDP problem with N arms. It is not giving the optimal solution. The only thing that it will give you in some sense is that at infinity, it will work well.
Because you say this in some sense, you're saying that every time I start solving, and then I'm getting MN. That's not what you're doing. You're going to do something else. You're saying, if there was such an MN, then I need to project.
Exactly. So now I will tell the algorithm using the projection operator. What is the algorithm to create a good heuristic on a multi-arm bandit? You have a M0 star, which is your empirical distribution, right? With N arms, okay? You do the projection. You can do the projection, right? It is giving you something living in the simplex. It's giving you a proportion of arms to activate in every state at time t. Be careful, it's a proportion. We are working with action 0, 1. So what we need to do is we need to do a rounding step to make sure to decide the number, the actual number, because the problem of the projection is not giving you integers. It's giving you probability. So then you use a rounding step to create integers and to actually tell you the exact number of arms that you have to put in state S. Then you use this control and you again observe your Markov chain. You again observe your Markov chain and so on and so forth. So the things that you have also to be careful is the projection. Again, I'm repeating myself, but is not giving an integers. And actually your n-arm bandit problem is working with integers. So you're obliged also to have these rounding steps. And a small summary of this algorithm is the following. You have your empirical distribution. So you have your observation. You do the projection. Then you do the rounding. And then you observe the next transition, the next empirical distribution. And actually, the key is there. Projection is just the operator, it's just a convenient operator that have good properties, but you can think of any map because the projection is basically doing interpolation. You want to create a map which is going from one measure space to another measure space that has the following property. You want the feasibility, right? This is what I said, to ensure that you will be able then to work in a space such that you will be able to work in the n-arm case, right? And you want also that at infinity, it's giving you the exact result. And the key point actually, even is actually to solve, to find P that is satisfying that. And even when we will do kind of machine learning approach where we don't know the transition probability, actually, the key things is, can you design just based on observation of my empirical distribution and my reward, P with these two properties? Because the moment you're able to design a piece that has these two properties, you are done because you know that it will converge. And this is the main theorem that, first of all, take any policy which is continuous and admissible. Then what's happening is when n is going to infinity, you will actually converge to the LP problem, right? So basically it's saying that relaxing the constraints is good when n goes to infinity. But be careful, you need an admissible policy. And if P is LP compatible, so what does it mean being LP compatible? It just means that your policy at infinity is exactly giving the right answer, is giving the solution of the linear program, then you are optimal. Okay, at infinity, you are optimal. And of course, people have designed more complex results where you have actual convergence rate, but they are actually a bit tricky. But I will show you basically the course of tomorrow will be first dedicated to do the proof of some simplest version of this theorem. I don't want to use all the heavy tools. I will especially focus there by adding some extra assumption. But if you want to see the real proof of the theorem, you can look at this paper from basically Shen Yan, which is a student of Nicolas Gast, where you have the real proof of the paper. And more complex proof, sorry, with more complex assumptions. And if you want to see a lot of different applications, just go to this paper, the Whittle index-based Q-learning, and just in the introduction, they list at least 20 applications of this kind of problem. Okay. So tomorrow, I will do the proof of this theorem. And then we will see more complex framework. Okay, that's it for today, I think.